Today we'll be talking about changing map representations. Last time we talked about what a change of basis matrix is and how to find them. Technically, we already learned how to find them in previous sections, but we restricted our attention to the specific case of representing a linear map with respect to, the linear map that we were trying to represent was exactly the identity map from a vector space to itself, whereas previously we learned how to represent a general linear map f from v to w, how to represent that with a matrix with respect to some pair of bases for the domain and codomain. So today we're going to be using change of basis matrices to take a representation of a linear map with respect to a pair of bases and get a new representation for that linear map with respect to a different pair of bases. So here's what I mean by that. So let's first start off with some linear map f from v to w and a representation of that linear map with respect to a pair of bases b and d for the domain v and codomain w. So notation, A is equal to the representation of f with respect to b and d. What that means is that the representation of v with respect to b, which just as a reminder is a vector where the entries of the vector we get as follows. So v, you can write it as a linear combination of the basis vectors from B, and the coefficients of that linear combination get thrown into a vector, which we call the representation of V with respect to B. So anyway, this vector, if I multiply it by my map representation on the left, then that gives me a new vector, and that vector will be the representation of f of V, now with respect to the basis for the codomain D. Great. So, like I said, today's question is, what if we want to represent f with respect to different bases, which we'll call b hat and d hat? And again, we will use change of basis matrices to do this. So just some foreshadowing to let you know what's going to happen. Basically, if we want to to represent a linear map, what I really want is this whole situation here. I want to take the representation of, so now I guess I would want b hat and d hat here. So now I would want a new matrix, which maybe we can call it like a hat or something, such that if I multiply the representation of v with respect to this different basis by a hat on the left, I should get the representation of f of v with respect to the other basis d hat. So the idea for what we're going to do today, and I'll expand more on this later, is we're going to start with our representation with respect to b hat, use a change of basis matrix, multiply by that to get to the representation with respect to b. So we go from the basis b hat to the basis b, and then we use our representation with respect to b and d of f to take us from b to the basis d, and then we do another change of basis matrix to go from the basis d to the basis d hat. So we have three different matrices, and we just kind of use those three matrices, take a product of those three, and that'll take us from b hat to b to d hat. And I'll explain more what I mean by that shortly. Anyway, let's get rid of these hats here. So let's do an example. All right, so here's the map I want to look at right now. So we're going to call it f, and it's from R2 to R2. Here the domain and codomain are equal. That definitely doesn't always have to be, but it will be for this case. F f is given by, takes the vector xy and multiplies it on the left by this matrix A, whose entries are cosine of pi over 4, negative sine of pi over 4, sine of pi over 4, cosine of pi over 4. Right, so f is represented by this matrix with respect to the standard bases for the domain and codomain. This is just coming from a general fact that anytime that you have a function is given by f of vector is equal to matrix A times same vector, then that map F is going to be represented by the matrix that you're multiplying by with respect to the standard bases of the domain and codomain. Here the standard bases for the domain and codomain, because the domain and codomain are both equal, the bases for both are also going to be equal. But in general, you could have like a map from R2 to R3. You just have a, I believe, 3x2 matrix. R2 to R3 would be 3x2 matrix. In which case you would have the standard bases for R3 and R2. Okay, so anyway. So A is the representation of F with respect to B and D, the standard bases for R2. I could have just gotten rid of this D and just wrote rep of representation of F with respect to B and B, but it doesn't really matter. Okay, anyway, what's so special about this matrix? So this matrix right here is called a rotation matrix. Multiplying by this matrix, this is what it means to be a rotation matrix, results in rotating a vector, in our case, pi over 4 radians counterclockwise. And so an example of that would be, so this right here, this whole term is f of 1, 0, right? F of 1, 0 says take our matrix, our rotation matrix, multiply it by 1, 0. And if I multiply this out, then this is in fact equal to cosine of pi over 4, sine of pi over 4, right? The first row times first column is equal to cosine of pi over 4 times 1 plus sine of pi over 4 times 0, and then similarly second row times that column is equal to sine of pi over 4. Cosine and sine of pi over 4 are both equal to the square root of 2 over 2. So I'm taking the vector 1, 0 and mapping it to square root of 2 over 2, square root of 2 over 2. So here's let me zoom in a little bit to get our picture of what's going on here. Sorry, this is a little bit small, but so we're taking the vector 1, 0, which is just pointing straight out to the right, and that is getting sent to the vector square root of 2 over 2, square root of 2 over 2, which you can see is there's a 45-degree angle there, or pi over 4 radians. So multiplying by this matrix in this case does give us a rotation of pi over 4 radians, and this holds in general for any vector xy. By the way, just a general fact, a rotation matrix is any 2 by 2 matrix that looks like cosine of angle, negative sine of angle, sine of angle, cosine of angle, where all 4 of those angles are the same exact angle. That's just what it means to be a rotation matrix. Anyway, back to the example. So just summarize real quick. F of vector is equal to rotation matrix times vector. The rotation matrix actually represents F with respect to the standard bases for the domain and codomain, which are both R2. And now I am, so now we want these, we have these different bases that are just given to us, and we need to find the representation of F with respect to these new bases b hat and d hat. So b hat has the vector 1, 1 and 0, 2 in there, and d hat consists of the vectors negative 1, 0 and 2, 3. Okay, great. Um, so to do this, I'm going to explain what we were talking about a little bit at the start of this lecture. Um, this is basically the picture that is going on here. So this diagram I think is really useful for understanding what's going on here. So up top, the first part of this, we have R2 mapping via F to R2. And F is represented by the matrix A with respect to the bases B and D. And that's why over here I put R2 with respect to B. And over here I put R2 with respect to D. So A represents F with respect to B and D. So that's what's going on in there. And then similarly down here, we're looking for a matrix M that represents F with respect to B hat and D hat. Okay, what's going on in the left and right columns? So remember, a change of basis matrix is a representation of the identity map from a space to itself with respect to two different bases. So this matrix P will be the change of basis matrix for the identity map with respect to B and B hat. And similarly over here, Q will be the other change of basis matrix for, now I'm thinking of R2 as being the codomain of F. So Q is going to represent the identity with respect to D and D hat. Okay, so again, in this picture, I have A, M, P, and Q are the matrices that represent all of the corresponding maps, and that's important. P and Q are change of basis matrices. Remember that change of basis matrices are always invertible matrices or non-singular matrices, and therefore I can always just go. So if I'm going from R2 to R3 to change the basis B to the basis B hat, I could do the reverse of that too. I could start with B hat and then go to B by doing P inverse. Maybe it's not completely obvious that the inverse of this matrix P is actually the change of basis matrix for the identity with respect to B hat and B, the reverse of B to B hat. But that is true, and that does work out. So let me just kind of write that real quick. So P inverse, just to summarize what I just tried to say there, if P represents the identity with respect to B and B hat, then P inverse represents the identity map with respect to B hat and B. So P changes bases from B to B hat, P inverse changes from B hat to B. Anyway, so I am just going to go ahead and write P inverse here, and just reverse the arrow going upwards. And so what's going on all on the outside here? So, yeah, let me change something real quick. I'm just gonna write, I'm gonna put W's here. This is a last minute change here. This is like the fifth time I've had to record this video, so I don't want to just start over again, so bear with me, please. I've had some technical difficulties, but anyway, we're just going to work with this. All right, cool. So what's going on here? So everything that's not in red is basically just copy and pasted from the previous thing, except for the blue arrow right here, which is just, I took this and I basically just replaced the arrow going this way in P with the arrow going upwards with P inverse. So we need to figure out what's going on with the red here. So, okay. So saying that P inverse represents this map right here means that if I take the representation of a vector with respect to b hat, I can multiply it on the left by p inverse and get the representation of that vector with respect to b. And so I'm just going to, instead of writing the representation of v with respect to b hat, I'm just going to write w. So w gets sent to the representation of v with respect to b, which is equal to w times p inverse on the left. Similarly, a represents this map f right here with respect to b and d. So here I have the representation of v with respect to b, which is equal to this. And I can multiply this on the left by a to get the representation of f of v with respect to d. And now I have the representation of a vector with respect to d. I could do a change of basis matrix to now get the representation of this vector f of v with respect to d hat. Sorry, let me put an arrow there. And how I get this vector is I just take what I have over here and multiply it on the left by the change of basis matrix Q. So to go from R2, to go from the representation of V with respect to B hat to get, to obtain the representation of F of V with respect to D hat, I want to multiply this representation on the left by a matrix M to get this representation. And we can see that we can just go along this way and just multiply first by P inverse, then by A, then by Q, all on the left. So we're sort of reading right to left here, right to left. And so this will actually be equal to M. Okay, so I haven't been reading the stuff in blue. Maybe I should have been, but anyway, so let's just go over what they're saying real quick. So we can replace P and P inverse, P with P inverse, and reverse that arrow in the diagram. That's what we said before. And to represent F with respect to B hat and D hat, we can just go around the diagram and multiply our representation by P inverse, then A, then Q. Note that we are reading with from right to left here. So our matrix M is not going to be equal to P inverse times A times Q. It's going to be Q times A times P inverse, and that's because we're reading right to left when we repeatedly multiply by a matrix on the left. Okay, so it is important to realize that you're not getting P inverse AQ here, you're getting QAP inverse, even though it looks like you might be getting P inverse AQ reading left to right. So you read right to left whenever you're doing matrix multiplication on the right, which is the same as function composition. Anyway, so all of this diagram chasing stuff was just to tell us that our matrix representation of F with respect to B hat and D hat, our different bases, can just be obtained by taking our change of basis matrix from B hat to B, multiply that by our representation of F with respect to B and D, multiply that by our change of basis matrix from D to D hat. So that's what we need to do. So let's go back to our example. So we have B hat is this basis, D hat is this basis, and B and D are the standard bases. So, okay, so P is supposed to be the representation of the identity with respect to B and B hat, right? So P goes from B to B hat. So we want P inverse, which goes from B hat to B. And in our case, it turns out that that's actually easier to find what do I mean by that? So, okay, so you can take this as just fact. I've just been kind of saying this out loud for a while now. The representation, the identity with respect to b hat inverse of that is equal to just really switching the roles of b and b hat to b hat, and then b. And remember that b is the standard basis. And representing a vector with respect to the standard basis is always easier than the other way around. So in particular, so the representation of a map with respect to b hat and b, I first, since I'm doing the identity, I really just want to represent each vector from b hat. I want to represent that, write it as a linear combination of the vectors from b. So 1, 1 is equal to this linear combination of the vectors from b. It's equal to 1 times the first standard basis vector plus 1 times the second. And 0, 2 is equal to 0 times the first basis vector plus 2 times the second basis vector. And so our representation of the identity with respect to b hat and b is equal to, now I just take these representations and put them into this matrix here. So 1, 1 goes right there, and 0, 2 goes right there. Note that the representation of, so let me put b and then e of a vector. The representation of any vector with respect to some basis b and the standard basis e, so e is like the standard basis. This might be like E2 or E3, depending on like which Rn you're in. This is always equal to b. So this like works out in this case that 1, 1, the representation of 1, 1 with respect to I see. I should have just said the representation with respect to standard basis. Yeah, this makes more sense. So what I'm really doing here is I'm saying that the representation of this vector with respect to the standard basis is just equal to itself, because the linear combination is just equal to 1 times vector plus 1 times vector. You throw that into the representation vector, and then you just get itself. It gets itself back. And then same thing happens for that. And that's why whenever the standard basis is on the right, this whole process becomes easier. So anyway, let's keep going with this example. I'm starting to ramble a little bit. Okay, so we found our P inverse. Let's find Q next. So Q is the representation of the identity with respect to D and D hat. So I take each vector in D and write it as a linear combination of the vectors in D hat. And I went ahead and did this for you. So because our standard basis is not on the right, this would a priori just be a little harder to do. So I write my standard basis vectors from D as linear combinations of the D hat vectors. And so 1, 0 is equal to -1 times first vector plus 0 times second vector. 0, 1 is equal to 2/3 first vector plus 1/3 second vector. And therefore, I can put these representations into this matrix Q to get our representation of the identity with respect to D and D hat. This is our change of basis matrix, changing between D and D hat. Okay, so I just told you what the answer was here, but an easier way to do this than like what you could have done here. So maybe you actually went ahead and figured this out by solving c1 times that vector plus c2 times that vector is equal to 1, 0, and then did the same thing for 0, 1, and then now you have a system of equations here that you can do some row reductions and get the answer that way. But that could be a little bit annoying. So here's an easier way to do that is to just use what we were doing before. So just find, instead of the representation with respect to d and d hat, find the representation with respect to d hat and d, because now the second one is the standard basis, and this therefore would be easier to figure out. And then we could just, this is a 2 by 2 matrix, and then we can easily take the inverse of that matrix. So let's do that. So to get this matrix, we first write the vectors from d hat as linear combinations of the standard basis vectors. And of course, that representation is just going to be itself. I get -1, 0 is represented by -1, 0. Throw that into Q inverse. And then 2, 3 is represented by 2, 3. And that'll be that column of Q inverse. I'm writing Q inverse here because if Q is the representation of this, then Q inverse is the representation. Q inverse would be this thing. So if Q is this, then Q inverse is this. So now that we have Q, we can use our formula for the inverse of a 2 by 2 matrix to give us this matrix right here. So just to recall that the inverse of a 2 by 2 matrix, A, B, C, D, is equal to, so first we divide everything by AD minus BC, and then we switch the diagonal entries here, A and D, and then the off-diagonal entries stay in the same place, but we make them negative. So in this case, what I would get is AD minus BC would be -1/3. Sorry, I should be taking the inverse of this. We should get -3 minus 0. So I should get -3 for AD minus BC. And then I switch my diagonal entries. And then my off-diagonal entries, I just take the negatives of them. And so this is what I get. And then I just distribute this -1/3 to everything. And this is my Q inverse, which is exactly what we got before. Great. So anyway, we found what Q is, we found what P inverse was, and we already know what A is. And using that diagram before, we can just say that A times multiplied by Q on the left and P inverse on the right gives us our representation of F with respect to B hat and D hat. So this is equal to this product. This was our Q, this was our matrix A, our rotation matrix, and this was our P inverse. So I just take the product of those three things, and so I don't think it's really worth our time to go through the calculations, but I'll keep it on screen here for anyone that wants to check that this is right. Go ahead and pause if you want to check all this. But what this comes out to is this matrix right here. So this matrix here is our representation of F with respect to our new bases B hat and D hat. Okay, so that was a lot of explanation. I think that the best way to really learn this is to do some examples for yourself. So I want you to try this example here. So F from R3 to R3, again, in this case, the domain and codomain are equal, but they don't always have to be. So F of xy is equal to y plus z, x plus z, x plus y. So first thing that you would generally have to do, I already did it for you, is to represent f with respect to the standard bases here. And so this you can just write as this matrix times x, y, z. So therefore, we can say that this map is represented by A with respect to the standard bases for R3. So what I want you to do is to find the representation for F with respect to this new pair of bases, which the B and D are both going to be equal. Oh, these should be hats. B hat and D hat. Yeah, so I want you to find the representation for F with respect to B hat and D hat both equal to this basis right here. So anyway, pause the video, try this problem on your own, and once you've had a chance to try it, then unpause the video and we will go over this. Great, so I'm going to assume that you've given this problem a shot and you know what sort of things you struggled with in the problem, or you know what you think the answer should be, and you know what you're going to be looking for in this. So let's do it. So here's what our picture looks like, again, our diagram. So I have R3 with respect to the standard basis. So A represents F, and so that takes me from R3 with the standard basis to R3 with the standard basis again. And P is going to be the P is going to be the change of basis matrix between E3 and B. And M is going to be the matrix that I want to represent the map F with respect to B and itself B. So here I have, like, instead of Q in my diagram, since E3 and B are the same over here, then Q would actually just be equal to P in this case. So we need to figure out what P is, and also P inverse, because I want to go up the diagram that way, then that way, then that way. So I need P for this part of it, and I need P inverse for this part of it too. So let me get rid of that. Okay, so which is going to be easier between finding P or P inverse? Well, probably P inverse, because P inverse would be equal to the representation of the identity with respect to B and the standard basis. So since the standard basis is on the right, this one will be easier to find. So let's write the vectors from B as a linear combination of the standard basis vectors. And I have them all here. So 1, negative 1, 0 is equal to 1 times E1 plus negative 1 E2 plus 0 E3. 1, 1, negative 2, again, is going to be represented by itself. 1, 1, 1 is going to be represented by itself. So now I put these representations, 1, negative 1, 0, 1, 1, negative 2, and 1, 1, 1, and for the columns of my representation, which is equal to P inverse. And now I just need to figure out what P is, and I get that just by finding the inverse of this matrix right here. So how do we find the inverse of a 3 by 3 matrix? Well, there is a formula for the inverse of a 3 by 3 matrix, but I don't think it's worth remembering. I think it's easier to just go ahead and, I mean, if you don't have a calculator or MATLAB or Wolfram Alpha to do it for you, you could always do it this way by row reducing the matrix first and simultaneously doing the same row operations to the identity and see, and then once you get that this is equal to the row reduces to the identity, then this should row reduce to the inverse of this matrix. So I won't go through all the row operations, but I'll leave them on the screen so that you could check them. I'm pretty confident that they're right. So I first did like row 1 plus row 2 to get rid of this -1 right here. And then I did row 2 plus row 3 to make that a 0. And then, so now it's an echelon form. And then, so I go ahead and make all the pivots 1, and then start zeroing out everything above it to get that this is a row equivalent to the identity matrix. And this is what I ended up getting on the right side of that after all of those same row reductions to the 3x3 identity matrix. So this matrix right here is the inverse of the matrix that I started with over here. So in other words, this matrix here is equal to the inverse of P inverse, which is therefore just equal to P itself. So I always recommend when you find the inverse of a matrix this way to check that it's right by just multiplying them together to see that you get the identity matrix. When I worked this example out myself, I made a mistake somewhere, and when I multiplied these two things together, I did not get the identity matrix. So it was a good check for myself so that I didn't, start recording this and then realize that I had messed up and have to, start over like a 7th time or something. Anyway, you can check this and make sure that it gets you the identity matrix, and of course it does in this case now. And so this is the correct matrix for P. So now I have P, and I have P inverse as well. This one was P inverse, and this one was P. So I have all this stuff in my diagram here. So again, my representation here, I'm just writing it's equal to V, goes to P inverse. Then I read right to left and multiply on the left by A, and then I multiply on the left by P to get from my representation with respect to B to my representation with respect to B of f of the vector that you started with here. So that tells us that M is equal to PAP inverse. Right, so I'm reading right to left here, so P inverse should be on the right, A should be right to the left of that, and P should be right to the left of that. And so to get our final change of basis matrix, I just have to multiply these three matrices together, and again, not particularly worth going through this calculation, but I'll leave it on screen if you want to check it. But if you multiply these three matrices together, what you end up getting, miraculously, is this diagonal matrix, -1, -1, 2 along the diagonal, and then zeros everywhere else. And this is a lot nicer than our original representation. Our original matrix representation was this matrix right here. Compared to this diagonal matrix, this is a lot simpler or better than A. And what does that mean? So over here, I kind of sketched out what I mean for this to be nicer or easier to work with than A. So, yeah, what do I mean by that? So, if I okay, f of b1, how do I know what f of b1 is? Where b1 is like the first basis vector from B, the basis B. Well, b1 is equal to 1 times b1 plus 0 times b2 plus 0 times b3. So 1, 0, 0 is the representation of b1 with respect to itself, B. Sorry, not itself, but the basis B. And so -1, 0, 0 is the representation of f of b1 with respect to B, because I can just multiply by my representation matrix on the left times my representation to get my new representation of f of b1 with respect to b. So yeah, this diagonal matrix times 1, 0, 0 is equal to -1. So I get first row times that column is equal to just -1. Second row times that column, 0 times 1 plus -1 times 0 plus 0 times 0, that's 0. And then similarly, third entry should also be 0. Therefore, the representation of f of b1 is equal to -1, 0, 0, and that's with respect to b. So this tells me how to write f of b1 as a linear combination of b1, b2, b3. So f of b1 is equal to -1 times b1. And then if I did the same thing with f of b2 would be equal to, so b2 is represented by 0, 1, 0, because that's equal to 0 times b1 plus 1 times b2 plus 0 times b3. So that tells me that f of b2, I can figure that out by multiplying this times 0, 1, 0, which would be equal to 0, -1, 0. Therefore, f of b2 is equal to -1 times b2. And then similarly, f of b3, I would just do the same thing with 0, 0, 1, and then I would be picking off that 2 in that'll be like going to the third entry, and so f of b3 is equal to 2 times b3. So anyway, this is really good because this is telling us that b1, b2, b3, these are all examples of eigenvectors, and -1, -1, and 2 are the eigenvalues associated to them. We'll talk more about that at a later date and time, but eigenvectors and eigenvalues are pretty important and get used all the time, especially in like engineering and stuff like that. They're just very important tools with linear algebra. So, yeah, anyway, so M is equal to PAP inverse, that's a diagonal matrix. And so this diagonal matrix represents our map F. So that leads to a definition. So we say that a map F is diagonalizable if there is a basis B such that the representation of F with respect to B in itself is a diagonal matrix. And that's exactly the situation that we had up here. The representation of F with respect to our basis B and itself was a diagonal matrix. We just happen to be handed the basis that does that for us, but a question we will try to answer later on is how do we find such a basis? So we can also extend this definition to just matrices. We could just say that a matrix is diagonalizable if there is an invertible matrix P such that PAP inverse is a diagonal matrix. So yeah, for matrices, this is this definition just says that we can do the same thing that we had up here. So we have M was equal to PAP inverse, and that gives us a diagonal matrix. So this matrix right here is a diagonalizable matrix. Okay. Cool. So, okay. That's the end of that example. I want to move on a little bit. So, definition. This is the last part of this lecture will be a little bit different, but so for same-size matrices A and M, we say that A is matrix equivalent to M if there are invertible or non-singular matrices P and Q such that M is equal to PAQ. And this is the same thing that we were working with before with, so if we have a matrix A that represents F with respect to one pair of bases, and then we change of basis matrices P and Q and multiply on the left and right by A to get a representation of F with respect to a different pair of bases. Sometimes you would have like a P inverse here or something, but if P is invertible, then P inverse would be invertible, and so this definition like still works just fine. But anyway, so changing bases, changing the bases for a map representation is one way of getting matrix equivalent matrices. So anyway. So some notes about this definition. Matrix equivalent matrices represent the same map with respect to appropriate pairs of bases. So if M is equal to P times A times Q, and M and A represent a map, well, let me just say that A represents a map, then P and Q are invertible matrices, therefore they are change of basis matrices. Therefore, PAQ also represents the same map that A represents, just with respect to the different bases that P and Q changed us to. Okay, this next note is pretty much a note on how to easily identify if two matrices are matrix equivalent. So left and right multiplication by an invertible matrix corresponds to performing row and column operations on A. We already talked about how left multiplication corresponds to performing row operations. We didn't talk as much, but we sort of hinted at, and all of the stuff that we talked about with left multiplication corresponding to row operations carries over to right multiplication corresponding to column operations. So all of that stuff carries over there. So right multiplication by invertible matrices also corresponds to column operations. Therefore, if A and M are matrix equivalent, if M is equal to PAQ, where P and Q are invertible matrices, then P and Q represent row and column operations done to A. So I can say that A and M are matrix equivalent if and only if there were row and column operations taking A to M. So as a quick example, matrix equivalents and row equivalents are different. So here's a matrix 1, 0, 0, 0, and here's a different matrix 1, 1, 0, 0. These are matrix equivalent because I can start with this matrix and I can do column operations to get to this matrix. Specifically, I can add column 1 to column 2 and get a new column 2, should be this, and I obtain this new matrix here. Therefore, this matrix and this matrix are matrix equivalent. However, they are not row equivalent, and this is because so any row operation that I do to this matrix here, in particular, if I multiply any row by a constant or add any multiple of row 1 or row 2 to the other, or do any row swaps. The second column is always going to stay a column of all zeros. So this column, no matter what row operations I do to this matrix, this column will always be a column of zeros, which of course is not the case for this matrix. So these are not row equivalent, but they are matrix equivalent. Here's a bigger example. Here's a rank 3 matrix. So I already put it in reduced echelon form. Remember, every matrix has a unique reduced echelon form. And therefore, every matrix is, every row equivalence class of matrices is represented by a unique reduced echelon form matrix. So this reduced echelon form matrix, I could do column operations to this to simplify it even more than it already has been. So in particular, I can take -4 times column 1 and add it to column 3 to make this entry a 0. I can do the same thing with column 2 to make this 2 become a 0. I can add -2 column 2, add it to column 3. So now this column will be all zeros. This column will still have this 1 over here, but I can switch this column with a 1 right here, switch that with this column of all zeros, and obtain this matrix here, which looks like a 3x3 identity matrix with an extra row and column of zeros added to the end. So our rank 3 matrix is matrix equivalent to this matrix with 3 1s along the diagonal and zeros everywhere else. And so this is a general theorem that holds. Any m by n matrix of rank k is matrix equivalent to the m by n matrix whose first k diagonal entries are 1 and all other entries are 0. So this general picture. So we have 1s along the diagonal, k of them if our matrix is rank k, and then everywhere else is just going to be a 0. So I got a little bit lazy and just put some big zeros on the off diagonal to just represent that everywhere on the off diagonal is just zeros. And how do you go about proving that? Well, I'll just sort of say it out loud. So every matrix is row equivalent to a matrix in reduced echelon form. So you put it into reduced echelon form and you get some 1s in your for your pivots. If your rank is k, then you would get k pivots, k non-zero rows, and then you can use your pivots to zero out anything that's to the right of them. So maybe there's like a 7 over here or something like that. Doesn't matter, because you can use this pivot and do column operations to make every entry to the right of it zeros, in the same way that you can use row operations to make everything below your pivots equal to 0 as well. So once you make everything to the right of all of your pivots equal to 0, then you can just do some column swaps to put it into the form that you want, just like we did in this example here. Okay, so a corollary to that is that A and B are matrix equivalent if and only if they have the same rank. And that's just because if you're rank k, then you are matrix equivalent to this. And if two matrices if two matrices are, if two matrices are, how do I say? yeah, matrix equivalent to a matrix that looks like this, then you can say what the ranks are going to be based off of how many ones there are right there. And so that would tell you that they would have the same rank. So anyway, don't want to talk too much more about that. I want to move on. So there are 4 equivalence classes of 3x3 matrices under matrix equivalence. There are a whole lot more under row equivalence. So row equivalence, there are infinitely many row equivalence classes, but for matrix equivalence classes, there are only going to be 4 of them, and you can count them just uh, by using the possible ranks that 3x3 matrices can have. So 3x3 matrices can have rank 0, 1, 2, or 3. Therefore, each 3x3 matrix is going to be row equivalent to one of these 4 representatives. So representatives of these equivalence classes can just be chosen to be the all 0 matrix with just a 1 in the first entry, 2 ones along the diagonal, 0s everywhere else, or just the 3x3 identity matrix. And these represent the rank 0, rank 1, rank 2, and rank 3 classes, matrix equivalence classes. Okay, so